Hello there, College Algebra 2 students from Avon High School, and to anyone else who might be tuning into my YouTube channel to get a little bit of help with their solutions of the systems of quadratic equations. We welcome you. And we're going to take a look at some problems here that focus around solving a system of equations where at least one of those two equations is going to be quadratic in nature. So if you're watching this video, it's very likely that you've been talking lots about quadratic functions, perhaps how to graph them. And it seems like the only next logical step is what happens if you have maybe a quadratic with a linear or possibly two quadratic equations, and how would you see them work with each other, interact with each other both graphically and algebraically. So we're going to go ahead and take a look at an example here, but prior to that, I want to kind of address a very important question. The underlying premise of this idea, located right here, it says, remember that the graphical interpretation of solving any system of equations, no matter what kind of equations you have, is to find the blank of the graphs of the functions represented by the equations. So if you think about that for a second, I'll clue you in on the answer. And the answer is to find the intersection or intersection points of the graphs. So first, we're going to go ahead and look at an example of a system of a linear and a quadratic function. So we got this example here where f of x is defined to be x minus 4. It's our linear function. G of x is a negative x squared plus 4x. Well, our first directive is to graph this system on the coordinate grid to the right. So we're going to go ahead and do that. I'm going to graph f of x in blue, and we're going to do this the easiest way possible by recognizing that this is a slope-intercept form. So that means we'll put a point at negative 4, and we will recognize instantly that the slope is a positive 1. So we have this up 1 over 1 relationship that we're going to be dealing with. Now, I cannot emphasize the importance of using a straight edge when you're going to graph systems of equations where one of them might involve a quadratic. And I think that this will become a little obvious to you here in just a bit. Now, I'm going to have a little bit hard time with the straight edge on the computer, so I'm going to cheat just a little bit, and I'm going to use the idea of a straight line tool instead. So I can probably get this line to traipse through these points with that slope of 1 as best I can to look a little bit something like that. And then I believe I promised you that I would graph this line in blue, so that's the next thing that I want to do. So let's take this line and say, hey, I would like to make you blue. So we've got that. And all truth be told, this line will head off in both the positive and negative directions forever. So oops, let me fix that there. And here we go. We're going to go ahead and put arrows at the ends. All right. Next up, we're going to graph our g of x. I'm going to do this one in red, and this one's going to be a little bit trickier because it is quadratic. There's a variety of ways to sketch this graph, one of which is to set up a long table of values. That's the way that I'm not wanting you to do. That's the way that we just tried to avoid with our students here at Avon. And we decided that we're going to go after the vertex because we have a very handy-dandy formula in which to do that, and that is to take the opposite of the linear coefficient, or in this case the 4, so opposite of 4, negative 4, divided by 2 times the quadratic coefficient, or in this case negative 1. And we know that that is going to be equivalent to the x value of our vertex. When we simplify this, we would get positive 2. And then when we continue to focus on the g function as a whole, we would input 2. Be careful, the negative sign is not going to be squared. So negative 2 squared is negative 4, plus 4 times 2, 8, would give us a y value of 4. So we would have a vertex at 2, 4. Once you have that vertex, you've got it made, because we have discussed about finding that value of a. In this case, we know that the a value in this problem is indeed negative 1. That tells us a little bit about this behavior, that this parabola will open downward, and the fact that the absolute value of a is 1 means that our y values will fluctuate by normal perfect square amounts. What do I mean by this? Well, I mean that when we go out 1 unit in the horizontal direction from the vertex, we will have transferred that change to 1 unit in the downward y direction. Downward because a was negative, 1 because that is the first perfect square. When we go out 2 units in the x direction, we would then go downward by 4 units in the y direction. And when we go out 3 units in the x direction from the vertex, we would go downward by 9 units. So we would have the ordered pairs 3, 3, and 1, 3. And then if we go out to the 2 units from the vertex, where x is 4, we would count 1, 2, 3, 4 units down. So we would land at 4, 0. And then we would land at 0, 0. And then if we were going to go out 3 units, 1, 2, 3, I'm going to erase that here in a second. So then we would have to go down 1, 2, 3, 4, 5, 6, 7, 8, 9 units in the y direction. So that lands us at 5, negative 5, and our counterpart would be negative 1, negative 5. I'm going to erase some of these extraneous marks. And then I'm going to do, to the best of my ability, the connection of all of those points so that we have what seems to be a nice smooth parabola. Again, I'll use arrows in this case as well. Now, in this particular example, something really wonderful happened. We kind of accidentally stumbled upon our points of intersection, which I'm going to label or mark in darker, bolder black here, so that they stand out a little bit. And that essentially will answer our next question. At what ordered pairs do the graphs appear to intersect? So we would say the point 4, 0, and the points negative 1, negative 5. It doesn't matter which order that you would express those 2 points, of course. And that would essentially wrap up the first part of this example. Now, I don't advocate using this method all the time because it's a little messy. You have to have a coordinate plane. You have to be, I don't want to say a good artist necessarily, but you have to be very careful in the way that you graph the parabola, because let's face it, when you graph the parabola, you are working in a freehand sort of mechanic, and you're at the mercy of how well you can connect those dots, and some of those dots can be very far apart. And the other thing I really don't like is there is no guarantee that the intersection is going to be nice integer value coordinates. And when that is the underlying answer, then this method is by far and away the worst way to solve. So we're going to look at an algebraic approach, and that's what this box here is below, or talking about below, and space below here. Set the 2 equations equal to each other and find the identified points of intersection. So because these 2 equations are each equivalent to some form of a y, f of x and g of x, those are like our y's, we essentially are allowed to take the 2 equations, x minus 4 and negative x squared plus 4x, or I should say take the 2 expressions to the right side, on the right side of each equation, and we would set those equal to each other. Now we just rely on our ability to solve a quadratic, which means we must set these equal to 0, right? That is one of our underlying principles at solving equations of higher degrees, must set equal to 0. I'm going to write that just to kind of remind everybody. So that means I will add the x squared over to the left. I will probably subtract the 4x over to the left, leave that negative 4 there on the left, and then we go about solving this quadratic equation by a variety of methods, my favorite of which is factoring. My philosophy with my students is if you can factor this in about 15 or 20 seconds, great. If you are unable to factor this in about 15 or 20 seconds, it's likely that it does not factor, at which point I would investigate using either quadratic formula or completing the square. I'm not going to give up on factoring this just yet because I have high hopes for this. If I use x and x, we could break 4 into 2 and 2, but I think it might be best to break it into 4 times 1 because I see that the sign here, negative, means we have to have opposite signs. The negative 3x here in the middle prompts me to make that 4 negative. Next up, I will use the zero product property. Many students may not write this step. It's quite all right if you understand what's really happening, but you're setting each of these factors equal to 0 because that's the only way their products can be 0. One of them must be 0. We don't know which one, so we set both of them equal to 0. And we get these two answers. Now, it's very easy for students to pat themselves on the back and say, yay me, I'm done. I've got this finished. Well, no, that's not really exactly the case because this question wanted to find the points of intersection and you've not found the y counterparts. So you will have to go back into one of the two equations. It does not matter which one. Pick the one that's easier. I think I know what you're talking about. I think you're all saying that f of x is probably the easier one. Yep, remember that f of x is x minus 4. And just simply plug in each of those points in for that x. Plugging in 4 gives you, of course, 4 minus 4, which will be 0. Plugging in negative 1 would give you negative 1 minus 4, which is negative 5. So then you could just kind of pair up those coordinates. The x that was 4 corresponds with the y that was 0, and the x that was negative 1 corresponds with the y that was negative 5. And what do we see? We see that we have the same answers from our graphing approach. Now, there's no question, in my opinion, that the better approach is to use an algebraic method because it's going to work every time and you want to get very comfortable with this, especially when it leads to answers that don't necessarily come out so pretty. So I wanted to take a look at a couple of other examples here, just so that you're going to be ready to go on the homework assignment that you're going to be working on. We're going to take a look at this first one here in the bottom of this particular page. It says the linear a function above intersects the quadratic function at two different points. However, this doesn't always have to be the case. So it says to solve these these systems below algebraically and interpret the results. So we're going to go ahead and do that the same way that we did above. So we're going to see that both of these are set equal to 0. Or I'm sorry, both of these are set equal to some function name that can act as our y. So I'm going to say that x plus 4 quantity squared is equivalent, with the minus 3, is equivalent to 2x plus 4. Now, another thing about this particular problem that's a wee bit, kind of problematic is that we will very likely want to expand out this quadratic. It's kind of a nuisance that it's not already expanded, so we'll do that, and we get x squared plus 8x plus 16. And we just really write everything else that we see. And then we go about our business of setting this equal to 0. So I'm going to subtract 2x over. I'm going to subtract 4 over. And I'm also going to consider this minus 3. So I'll tell you what, let's do this. Let's call this 13 minus 4. And when all is said and done, we should have 9 there. Now, when we go about factoring this, something interesting happens. We would get x minus 3 times x minus 3. Or we could say x minus 3 quantity squared. Either way, it does not make any difference because you're only going to produce one answer for x. X is equal to positive 3. And at which point you decide, hey, which of these two functions you want to plug in to find the y. It won't make any difference. You will get the same answer. So we'll pick the easier of the two, which is the g of x, and we find out that we get 10. And I'm double checking some things here to make sure that my work is good. And I think we're good. I think we're good. So what's going to happen here is, actually, I take that back. I take that back. Some of you are probably thinking, no, it's not good. It's not good. Just making sure that you're awake. I want to say I made a mistake right here. I think this should have been a plus 6 because 8x minus 2x is 6x. And this 13 minus 4, this should be a plus 9. So it doesn't mean that we have to change a whole heck of a lot. I apologize. This should be an x plus 3. So we're going to go ahead and make this negative 3. All right, so I'm going to go back and kind of retrace my steps here for g of x, we're going to find g of -3. So that would give us 2 times -3 or -6 plus 4. So I'm going to change my answer for the y to be -2. Again, I apologize about that. So our final answer is going to be -3, -2, which means we have one answer. Only one answer is happening within this particular problem. And in short of having to sketch this and demonstrate this, it's something that I would certainly encourage you all to do. But it's very likely whenever you have one answer like this, the parabola that you're talking about and the line have a very special relationship. It's called a tangent relationship. And you're probably looking at a situation where the line just lies slightly below the parabola, so it would only brush it and hit it at one spot. So I would encourage you to take a look at the sketch of these two graphs just to confirm that particular notion. Now, I'm not going to work through this next example, but I want to at least clue you in on the answer. And for my students who are working this out in class tomorrow, while I'm away and the substitute is there, I want you to confirm that you would get no solution in this situation. So there's something that must happen as you are trying to solve for x and y that doesn't produce anything very significant. And graphically, I'm certainly aware of the fact that you could see that by taking a look at this upside downward parabola that would exist, the g of x with the negative coefficient for x squared, and the linear equation above, which I believe also has a negative value, a negative slope, and they very likely might have a relationship like that. Now, you will find out that in order for this particular solution, no solution, to arise, you're going to probably find yourself dealing with some imaginary numbers. So that's certainly going to be the case. All right, got one more example and then I'm going to close out this video. And this next page says, in a similar way, systems of two quadratic functions can also be solved. So they want us to solve each of the following systems and they want us to graph them on the calculator to verify the algebraic results. I'm going to leave that for you. But we're going to go ahead and take a look at the second one here in the upper right column. And at the same time, we want to keep in mind that they're asking us to leave all the irrational values as decimals, rounded to the nearest thousandth. So we'll talk about that when the time comes. Now, in this particular instance, once again, you have your two equations that are both set equal to some form of f of x. So we're going to go ahead and allow ourselves the liberty to set the two equal to one another. So we'd have -1/2 x squared plus x plus 3/2 set equal to x squared minus 4x. Okay, now from here, we're going to go ahead and get x's on one side. I'm going to do something a little different. I'm going to get my x's on the right side because that way I can guarantee a positive value. Now, it's not going to be a pretty positive value because I have 1x squared plus 1/2 x squared, which is 1/2 or 3/2 x squared when I add this over. I'm going to subtract x. I'm going to get -5x. I'm also going to be very careful not to make a silly mistake like I did in the previous problem. And then the final piece is this positive 3/2 that I will subtract over to give me a -3/2. So that should be correct in setting this equal to 0. Now, you certainly could dive right into trying to factor this, if it does factor. I don't even know if it does or not at this point. You could jump right into the quadratic formula with all these ugly fractional values, especially of a and c. But a trick to kind of alleviate any headaches with fractional values is to multiply through by the common denominator. So we're going to multiply by the least common denominator, which in this case would be 2. It's the only denominator, in fact. So once we do that, we would have 0 still on the left side. After all, 2 times 0 is 0. And then when we multiply the right side by 2, we essentially see that with everything with a new 2 multiplied by it, we have 2's that could cancel in the fractions, leaving us with 3x squared. Now this minus 5x doesn't have a 2 in the denominator, so he'll take on the normal multiplication. And then the 2's cancel for the last fraction, leaving me with a minus 3. Now, in this particular problem, I'm going to go ahead and tell you that this will not factor. You could take your 15 seconds or 20 seconds, play around with various combinations of 3's, but you're not going to be able to get that term in the middle of minus 10x. So I'm going to choose to go ahead and use our wonderful friend, the quadratic formula. In the quadratic formula in this problem, my a is 3, my b is negative 10, and my c is negative 3. So what that means is I will have my x equivalent to the opposite of b, which is negative 10, plus or minus the square root of negative 10 squared minus 4 times 3 times negative 3. That's the 4ac. I can close off my square root now, and I can put this all on top of 2 times our 3. So now we are going to continue simplifying this rather robust fraction and get to positive 10 plus or minus, and we essentially would have 100, double negative is a plus, and 4 times 3 would end up being 24. So we'd have 124, I believe. And then all of this would be divided by 6. All divided by 6. So when we do our remaining simplification, 10 plus or minus the square root of 124 all over 6. Now, we need to start kind of thinking about ways that we want to express this x. And I know the directions do want us to move towards the calculator, but I don't want to sort of paint a broad stroke and say that's the best way to do this. Because if we start plugging this into a calculator, we're going to have no choice but to round our answers, and that's never a best practice. So I'm going to at first ask us to see if we could simplify this square root of 124 by finding a perfect square that is a factor. And we look at this a little bit, we kind of think of one of our first perfect squares, which is 4. And we can see that 4 is going to go into this. 4 goes into 12, 4 goes into 4 evenly. So if we broke this into the square root of 4 times the square root of, it would be what, 31, I believe. The square root of 31. So that means we would end up with 10 plus or minus the 2 rather, times the square root of 31 all over 6. All over 6. So at this point, we are now going to redo a little reducing, I guess, and we could call this 5 plus or minus the square root of 31 all over 3. Now, I wouldn't wish this on my worst enemy. I wouldn't wish anyone to say, okay, well, that's the x value. Let's go ahead and plug that in and get some y value with some radical expression, because it's just not a lot of fun, let's face it. So at this point, what we could do is we could go into a calculator and we would go ahead and express this as a decimal. And I'm going to kind of leave this exercise for you guys. You would enter this into the calculator as 2 different possibilities. 5 plus the square root of 31, divide by 3, and then re-enter it as 5 minus the square root of 31, all divided by 3. Now make sure, depending on the calculator model that you are using, that you make sure that the entire numerator is divided by 3. You can do that by using parentheses around the numerator, or some of your calculators have a built-in sort of fraction key, which is awful nice in order to make sure that you get these problems correct. You would round that to 3 decimal places, and then from there you would continue to use your calculator to plug those 2 particular decimals into either of these 2 equations, whichever one you want. They're both fairly ugly because they're quadratic, but you might think g of x might be a little bit easier to work with. So square the answer, subtract 4 times that answer each time for each of these two guys that you get, and pair them up in some nice ordered pairs, all rounded to 3 decimal places. And when I get back in class on Wednesday, we're going to double check and make sure that this is correct. But this is really the worst thing that's going to happen to you, a problem such as this that's going to have rather unpleasant answers. So at this stage, I want you to go ahead and embark on the homework. The substitute will definitely help you, guide you to tell you exactly how far to get up to. And in class tomorrow, we will talk about some application story problems involving these quadratic systems. Yes, story problems. I know you're looking forward to it. Anyhow, thanks for watching, and I'll see you very soon.
I got this feeling inside my bones.